Hello, my name is Li-Hsing Yen. Today I'm going to present my paper in ICC 2022. Okay, the title of our paper is Distributed Approach to Adaptive SDN Controller Placement Problem. My name is Li-Hsing Yen. The outline of this paper. Okay, so SDN or software-defined networking is a strategy that decouples control plane from data plane. In SDN, we have controllers which learns of network topology and decides on routing for traffic packets. And we also have SDN switches, which identifies packet flows and applies filtering and routing rules to flow packets. Of course, we can have multiple SDN controllers for a single SDN network. Here, this switch has two controllers that manage this switch at the same time. This is for purpose like controller resilience and also for load sharing. If we have multiple geo-distributed SDN networks like this, then we could determine where to place SDN controllers. In this example, we have three geo-distributed SDN networks, but we only place two SDN controllers, one here and the other here. This location, although we have SDN switches, we do not place a SDN controller. Okay, we use only two controllers. That we could minimize the deployment cost. So in a large area like the United States, we may have multiple geo-distributed SDN networks like this. Then we determine locations to place SDN controllers. These controllers will manage nearby SDN switches. So the problem, controller placement problem, or CPP, is to determine controller locations. The objective is to minimize overall placement cost. However, we should meet all constraints like the controller switch latency, intercontroller latency, and the controller capacity. Okay, this problem is in fact a variant of capacitated facility location problems. We must consider several factors in this problem, like the numbers of controllers. This is what we want to minimize. And we should consider a constraint. The switch controller latency should not exceed a threshold. Also, we should consider controller capacity as a constraint. We should consider traffic load of switches, which could be heterogeneous. Each switch may need a number of controllers to manage it. It's for resilience, okay, for tolerance. It's a requirement. And we also have a constraint that is intercontroller latency. If two controllers manage a common switch, then the distance between these two controllers should be small enough. Okay, the motivation in this research is to develop an autonomous adaptive controller placement approach. Okay, the motivation is most existing approaches to CPP assume static network topology. So they cannot easily handle change of network topology. Change of network topology, like a control or link value, can make existing solutions invalid or suboptimal. Of course, we could reconstruct a new solution every time we have a controller or link value, but this approach is not time efficient. Another motivation is that we may have a variation of traffic loads over time. This condition may make the static solution suboptimal. So we propose an autonomous gain theoretical approach. In this approach, agents make local and independent decisions to decide whether to place a controller locally. So this approach could easily adapt to values or changes in a distributed manner. Okay, the problem formulation. The objective is to minimize the number of controllers. Here, yi is an indicator variable where, which is one if controller is indeed placed at the location I. We have multiple constraints. For example, we should place a controller at the location I so that the controller at the location I could manage switch at the location J. Okay. Xij here, an indicator indicating whether controller at location I manages switch at location J. And the requirement for controller resilience, the number of controllers that manage switch J should be equal to Tj. Tj could be larger than 1. It's for resilience, for fault tolerance. More constraints about latency and capacity. We have switch controller latency. This is to say, if controller I manages switch J, then the in-between latency should not exceed a preset threshold. If two controllers here, I, J, IK are two controllers that manage a common switch at location J, then their in-between latency should not exceed the threshold CC max. And controller capacity, which means the load of switches placed on a controller should not exceed the controller's capacity. We model it as a game, controller placement game. Here, players are agent for each possible controller location I. Each player's strategy is to decide whether to manage each switch. So his strategy is in fact a vector. Okay, Xij here is 1 if a controller I decides to manage switch J. Stretch profile is a collection of all agents' decisions. Okay, it's a tuple X. And based on that, we define 3 games: basic CPP game, prioritized CPP game or PCPP game, and quick PCPP game. Okay, the basic CPP game. In that game, we define the utility of agent I to be Ki times the rest of this equation. Okay, here Ki is 1 if the capacity constraint is met. Okay, so that we can have the profit. Okay, denoted by this the later term. Okay, but we should also meet the switch controller latency, and also if the constraint is met, then we could earn the profit alpha here. Another constraint is about the intercontroller latency. Okay, beta here represents the cost, which is less than alpha. Okay, the intercontroller latency is denoted by CONij. Okay, it's 1. If no other controller that manage the same switch J as controller I has a latency that is larger than the constraint. Okay, in the paper, we proved that this gain is stable because this gain is exact potential gain. That means there exists an exact potential function phi, okay, defined as this, such that actually this function is consists of two parts. So the first part is a exact potential function for conjugation gain. And the later part is the exact potential function for self-motivated gain. And a linear combination of these two functions is also an exact potential function. Okay, this gain works, but it has a limitation. That is the Nash equilibrium. That means when the game stops, we may not have an optimal solution. For example, here we have 5 possible controller locations, and we actually placed 4 controllers to manage 4 switches. This is too much. Okay, but because this is Nash equilibrium, so we cannot make any improvement on it. Okay, we need 4 controllers. And an optimal solution to this scenario is on the right-hand side. Actually, we only need 2 controllers. Okay. So to overcome this limitation, we propose another gain. We add priority to controllers. The basic idea is controllers that have managed more switches have a higher priority than the others. Okay, we define priority like this, and we change the definition of several functions like G, change it to this one. Okay, in the modification, when the controllers has to make a decision, he only cares controllers with equal or higher priorities. We also have to modify the definition of CONIJ from this to this. Okay, and the benefits of the modification is that for the same scenario, which we have 4 controllers, we could, through a series of decision making, we could arrive at the situation where only 2 controllers are needed. Okay, we have conducted extensive simulations for performance evaluation. Here is the simulation setting. Okay, for static topology, we compared the 3 games with existing approach here. And on the left-hand side, we can see that the number of active controllers, okay, is lowest with the priority gain, okay, which is good. The basic gain does not perform well. And the counterpart, the non-gain approach, is somewhere in between. On the right-hand side is the number of state transitions. The basic gain need is the fewest number of state transitions. On the other hand, the priority gain needs more transitions. Okay. Then we consider the impact of link failures when 1 to 8 links fails. Okay. The priority gain still needs the fewest active controllers, which is good. The basic gain does not perform well. And the counterpart is between these 2 extremes. On the right-hand side, we can see the percentages of affected nodes. Okay, the game-based approach, all these three game-based approach do not need all nodes, all agents to be involved in the decision when link fails. Okay, so you can see that even with 8 link failures, we have less than 60% nodes have to make a new decision. Other more than 40% nodes remain do not change their decisions, do not change their controller placement decisions. Okay. Okay, here shows the impact of controller failures. Okay, we have 1, 2, 3, 4 controller failures. As you can see on the left-hand side, the priority games needs more active controllers as the number of controller failures increases. On the other hand, the basic game actually needs less active controllers when the number of controller fails. The reason is the basic game actually plays more than needed controllers. So when controller fails, okay, actually the redundant controllers is removed from the network. So the number of active controllers actually decreases. Okay. And then the counterpart, okay, quite like the priority game. On the right-hand side, we can see the percentage of affected nodes. The basic game performs the best. The priority game does not perform as well as the basic game. Okay, the conclusion. We have proposed 3 game theoretical approaches to controller placement problem. These 3 games are basic CPP, PCPP, and quick PCPP. The basic CPP game has the shortest convergence of but activates the most controller. The PCPP game activates the fewest controllers, but also incurs the longest convergence time. The quick PCPP game is a trade-off between these 2 extremes. Okay. In all proposed game-based approaches, link and node failure only affect a part of nodes in the network. Okay, that's it. That's the end of my presentation. Thank you.